Okay, we're going to talk about solving for zeros in polynomial equations, and we have all of these theorems that help us do that. And I've kind of listed them all out here, and I'm going to talk about them real quick before we do a couple examples. I put these in kind of the order of importance to you. Okay, and it's also maybe the order you would want to go about things. You know, these last four are just helpful, okay? You know, remember, we are looking for the zeros of the polynomial equation, but if we can reduce these to a quadratic, you know, where the degree is 2, then we wouldn't use these theorems anymore. We would just start doing the quadratic formula or factoring, okay? So these last four are more of just help, you know, just things to keep in mind. The fundamental theorem of algebra is you should always start with that when you're looking at a polynomial equation, because the degree of that polynomial that you're trying to solve is how many answers you're looking for, okay? So, you know, if you're looking at a polynomial with x cubed, then you're looking for 3 zeros. If it's a polynomial to the 5th power, then you're looking for 5 zeros, and so on, okay? The next thing is the rational zero theorem, and this is really the big one for what you're going to be doing, because when you find all of the possible rational zeros, that's your starting spot, because then you're going to take those zeros, those possible rational zeros, and start doing synthetic division on your original polynomial so that you can hopefully find one. Okay? Now, I would do the Descartes rule of signs before I start doing my synthetic division with my possible rational zeros, because that's going to tell you how many potential positive and how many potential negative zeros there are. Now, again, the rest of them are more just things to keep in mind, okay? Because you're going to be using all these possibilities that you got from using the rational zero theorem, and you're going to be plugging them in. And you want to keep an eye on the signs that are produced, because if you get all positives, that would tell you, okay, don't go any further up. That's the upper and lower bound theorem, right? If all the quotient and the remainder is all positives, that would be a place to stop, okay? You know, if you notice that you're using just integers, you know, to try, you know, you take some integers from your rational zero theorem, and you notice that the remainder of 1 is positive and then the remainder of the next one is negative, then that tells you that in between those two numbers there is a 0, okay? And that's how the location theorem would help. Okay, and so then you could look to see, well, is there any fractions that could possibly be zeros that I could try that are in between those two numbers. Okay, and then the conjugate zero theorem, that one is more to say, you know, if I find an irrational zero or an imaginary zero, then I know its conjugate is also a 0. And so this is kind of the very last one, and it usually is going to show up more with the quadratic equation. Okay, so there's a whole bunch of stuff going on here, but really this is the big important one, okay? And this is a good starting spot. Everything else is just going to help us along the way. So I'm going to do a couple of examples of how I would go about doing this. So here's the first example we're going to look at, and we're going to solve this function for its zeros. So we're going to go through and I'm going to show you what I do to use all of these theorems. First thing you want to do, though, is to make sure that you're in descending order and figure out whether or not you're skipping any terms. And that's just so that you're aware of what's going on. You know, once you start using the synthetic division, you don't want any surprises. So everything checks out. We don't have any skipped terms. Now, we are finding the zeros of this polynomial function, and those are found on the x-axis. And what you should think of is that anything on the x-axis, the y value is 0. And remember, f of x stands for y. So what we're really doing here, we're going to change this into an equation, and we're saying when y is 0, let's solve for x. Okay, so we're really solving this equation for x. So the first thing I'm going to do is use the fundamental theorem of algebra. Okay, and so all I'm going to do is look for the degree of this polynomial, and I see it's 3. And since it's 3, the fundamental theorem of algebra tells us that we're looking for 3 zeros. Okay, now we're going to go through all of this, and we really only need to find one using synthetic division because our quotient will end up being a quadratic, and then we're just going to find the other two by either factoring if possible or the quadratic formula. Now let's use the rational zero theorem. Okay, and again, this is talking about the constant term and the lead coefficient. Now these were called P and Q. P referred to the factors of the constant term, so let's list those out. So we would have plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Okay, and then Q referred to the factors of the lead coefficient, so plus or minus 1 and plus or minus 2. All right, now we're going to use these because we want to figure out P over Q. And these are going to be all of our possible rational zeros. Okay, and so there's kind of a lot, not too bad here. And again, I like to start with the denominator and kind of put that to all the numerators. So the first group is going to be plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Okay, now I'm going to move on and use this as our denominator and distribute that to all of these. Now if there's a repeat, I'm not going to rewrite it. In this case, there is not going to be any repeating. But we would get plus or minus 1 over 2, plus or minus 3 over 2, plus or minus 5 over 2, and then finally plus or minus 15 over 2. Okay, and so these are the big ones right here. These are the ones we're talking about. Okay, and there's a lot, right? 1, 2, 3, 4, 5. There's 16 possible rational zeros here. And so our only option right now is to start, doing synthetic division with these and with the original function here and see what happens. And so we're going to use the rest of these theorems to help narrow it down. So to help us narrow it down, let's start with Descartes' rule of signs. Okay, so we're just going to count the sign changes in the original here. Okay, and so we go from positive to negative, so there's 1. We go from negative to positive, so there's 2, and then we remain positive for the rest of the way. So since there are 2 sign changes, that tells us that there is either 2 or 0 positive real zeros. Okay, and so to really use this well, we're going to find f of negative x, and I'm just going to rewrite this. And again, when you're plugging in negative x, if it's an odd, it's going to change the sign of the term. If it's even, it's going to leave it alone. So we would have negative 2x cubed minus 9x squared minus 4x plus 15. All right, now we're going to count the sign changes. Well, we're negative all the way to the end, and so that's telling us that there is going to be one negative real zero. Okay, so this helps because I'm going to start looking at my negatives first, because maybe there's no positives, so it'd be silly to start working through all of those positive zeros that we just found. So that's how Descartes' rule of signs can, lead you in the right direction. So again, I'm going to start going through the rational zeros that we came up with and see if we can reduce this thing, find one of the zeros and reduce it to a quadratic. And again, I'm going to start going through negatives, and I start with the easy ones. I'm going to start with -1, and if that one doesn't work, I'm going to go to -3 and then to -5. That way I don't have to deal with fractions, and if I notice the remainder sign change in between those, then maybe I'll start looking at the fractions. So I'm just going to grab -1 because that was our first one, and I know from Descartes' rule that there's going to be a -0. So let's try it. Okay, and so we got lucky. Look, right away, there's a remainder being zeros tells us that -1 is one of the zeros, and that's great because now we're almost done, and we have this as our remaining quadratic. So, let's keep our eye on that. And we have 2x squared minus 11x plus 15 left over. And I'm just going to use the quadratic equation and or factor this if we can, and find our other two. Now we got lucky, right? I mean, the very first one we chose was one of the zeros. But if it wasn't, then we would just have to move on until we found one. Okay, so we're just going to solve this like we would any other quadratic. This one does factor, but if it didn't, we would just use the quadratic formula. Or if you're just more comfortable with the quadratic formula, go ahead and use that. But I'm just going to go through the steps of solving this. And we're going to see that our two factors are x minus 3 and 2x minus 5. We're going to set those equal to 0. And solve. Okay, so here's a 0, here's a 0, and then also don't forget about the 0 of -1. So we've found all three zeros. Now we're going to take a look at the graph just so you can see that what it would look like. Okay, so here's the graph of our function, and you notice that it does cross the x-axis at -1, at +3, and then at +2.5. Okay, so we're going to look at this quartic, and again we're going to check, make sure it's in descending order, and it is, and there's no skipped terms, so we won't have any surprises later on. And I'm going to rewrite this with y being 0, and we're going to run through and we're going to find the zeros to this polynomial equation. Okay, so by the fundamental theorem of algebra, I know that we're looking for 4 answers. Okay, so let's list out all of our possible rational zeros. And so the first thing we're going to do is look for p, right? And again, p is the factors of the constant term. So it could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay, and then the factors of the leading coefficient are plus or minus 1 and plus or minus 2. So for our possible rational zeros, we would have plus or minus 1, plus or minus 2, plus or minus 3, 4, 6, and 12. And now I'm going to use 2 as our denominator and get plus or minus 1/2. 2 over 2 is 1, so I'm not going to repeat the plus or minus 1, but then plus or minus 3/2. 4 over 2 is 2, so we already had the plus or minus 2, so I'm not going to rewrite that one either. 6 over 2 is 3, we already have that one, so I'm not going to rewrite that one either. And then 12 over 2 is 6, and so here's all our possible ones that we would have. So in order to help us narrow down what we're looking for, let's use Descartes' rule of sign. And so we're just counting the sign changes. And right, we're positive until we get here, so then there's 1 negative. We stay negative until we get to here, and so there's our second sign change. So we know that there are either 2 or 0 positive real zeros. Alright, so now let's check f of negative x. Again, I'm just going to change the signs of the odd exponent terms. So we have 2x to the 4th minus x cubed minus 17x squared plus 16x plus 12. And again, we're going to count the signs, the sign changes. So positive negative is 1, negative to positive 2, and then it stays positive. So there are 2 or 0 negative real zeros. Okay, so this didn't tell us as much as it did in the last example, and so we can really feel free to start wherever we want. And while we do this, we're going to keep our eye on any remainders that we may get, because that's going to give us a little bit more information, and we'll use those other theorems when we get there. So since Descartes' rule of signs didn't really give us any real place to start, I'm just going to start with the easy numbers and go 1, positive 1, negative 1, positive 2, negative 2, and use all the integers. And again, if I see any signs change on the remainder, then maybe I'll check one of our possible fraction zeros. That's all you can really do. So we're going to start with positive 1 and see what we get. Okay, so positive 1 is not a 0. I'm going to kind of keep an eye on the next one I choose and see whether or not it's a different sign. So let's go and try with negative 1. Okay, so we know that negative 1 is not a 0, but if you saw what happened here, we went from a negative remainder to a positive remainder. So we're thinking of the location theorem right now, and we know that there has to be a 0 between negative 1 and 1, because otherwise it couldn't have gone from y values of negative to y values being positive. Okay, so if you remember our list, what are some of the values in our possible rational zeros that were between 1 and negative 1? Well, we had negative 1/2 and positive 1/2, so hopefully that's going to be one of them. So let's just try it out and see what we get. So we'll try positive 1/2. Okay, and we already found it, so that's great. There's only a couple steps here, and we found one of our zeros. So let's write that down. We know that's for sure. So, and now we're going to take this and work with this instead. We don't need this part anymore because we found already one of them. So from here on, we're going to deal with 2x cubed plus 2x squared minus 16x minus 24 equals 0. Okay, now the original list of possible rational zeros are still the ones we want to work with. There's no reason to restart here. We've already gone through 1, negative 1, and 1/2. Okay, so I'm going to jump back to the positive integers. And again, I'm going to keep my eye on any remainder sign changes or zeros. Okay, so I'm going to start with positive 2 here. Okay, and since this is a negative 32, we know 2 is not a 0. And, one of the options is to continue on this way. We already know that we have a positive 1/2, so we know that there is another positive 0, because that's what Descartes' rule said. We can't just have one. It was either 2 or 0. And since we've already found a positive, it was positive 1/2, then we know we need another positive. So I'm going to go ahead and try 3. Okay, and it so happens that 3 is also a 0. So now we found 2. We have x equals 3 and 1/2. And now we have quadratic 2x squared plus 8x plus 8 equals 0. And we can use the quadratic formula, but this one factors, so I'm going to factor again, but use the quadratic formula if you want. We can divide everything by 2 here, which is a nice move. So we really have x squared plus 4x plus 4 equals 0. And now we're thinking of factors that multiply to give us positive 4 and add to give us positive 4. And so we actually have x plus 2 twice, but that's okay. There's nothing that says that you can't have a repeated 0. And they both give us negative 2. And so our other zeros are negative 2 and negative 2. Okay, so this isn't the worst thing in the world. It's a little time consuming, but there's a lot of information that you can use if you really understand how functions work in the coordinate plane and what you're looking for. Okay, and here is the function that we just solved for, and I had to zoom way out so you could really see, the majority of it. But here's our two zeros, and that's at both of them at -2. We have a 0 here at 1/2 and a 0 here at 3.